Okay, so today we will start with some so today I will start with some motivations. I say something about the content of the lectures. And what else? I will try to show you some paradigmatic systems. That we would like to describe with our approach, and this should keep us busy for 1 hour basically. And during the second hour, I would like to describe a quick review of quantum mechanics, very quick. And say a few things about, in particular, measurements. Okay, so this is the plan for today, and in particular, in the content of the lecture, I will try to tell you a bit more about what I'll do in the following lectures. Okay, so unless there are already questions, let's start the discussion. So let's start with the motivations. So I imagine everybody in the audience has already heard about quantum mechanics. And what you learn in elementary lectures on quantum mechanics is how to solve some simple problems. Like, well, the things you learn, maybe one of the first is the harmonic oscillator. And then the hydrogen atom, and maybe a few other systems. And then when you do solid-state physics, you talk about phonons in solids, which is essentially the harmonic oscillator again. But what is characteristic of these elementary lectures is that you consider these systems as isolated. And this is, of course, an ideal view of those systems. Even for the hydrogen atom, as you know, if you would like to make a really serious work, you would have to consider this as some part of quantum electrodynamics, at least, even if you consider that the proton has no structure and whatsoever. And so all the beautiful stable orbits that you find, the Bohr orbits that you find when you solve the Schrödinger equation, in fact, you are coupled to the degrees of freedom of the quantum field, and of course everything decays to at least to the ground state. Okay, so even these systems, even an hydrogen atom, and of course you can observe the energy levels and all that in experiments, and they are just fine, and it's an excellent approximation for reasonable amounts of time to consider the hydrogen atom as an isolated system. It's not really true. And even if you're in outer space wherever, you're always in a bath at basically 3 kelvins of photons. So nowhere in the world are you really isolated. And then the question is whether or not the fact that you're not really isolated is important for your system over the time scales you want to look at it. And it depends very much, and as I said, in certain circumstances, it's a perfect approximation, and almost perfect approximations, and in others, it's a very bad one. And open quantum systems deal with this situation. There is at least one situation in which clearly you cannot consider the system as isolated, and it's measurement. And you may think it's a bit bizarre to put together the notion of an open quantum system and to talk about measurement. If you think about an open quantum system, as I said, for instance, even in outer space, you have the relic photons at 3 degrees Kelvin. So, and in a room or whatever, you would think that you have your system and it's put in contact with a reservoir, a thermal reservoir, a heat bath. And you can ask yourself what this has to do, if at all, with measurement. And in fact, one of the messages I would like to convey during these lectures is that for Markovian open quantum systems, being in contact with a reservoir or being subject to measurements is exactly the same thing. So measurements and contacts with reservoirs are basically the same thing. So this is one of the, if there is only one thing to remember about this lecture, is that this is the same as being in contact, essentially, in contact with a reservoir. Or even with several reservoirs, if you want. Okay, so, or being open. And this is true, in fact, especially for Markovian systems. For non-Markovian systems, frankly, I don't know the answer. I guess this is still closely related, but I don't know. Okay, so this idea, of course, of measurement and being open is, however, familiar somehow. We all know that when we toss a coin or something, or throw a dice, we don't find a superposition of head and tails or whatever on the table. And one of the arguments you can give is that even the interactions with the air surrounding the coin is more than enough to destroy all coherence and all that, and to have a definite answer when you toss your coin. Okay. So basically what we want to model is the following situation, where you have something which I always try to always call sigma, which is the system, and it's part of something which I will call the universe. And sometimes the universe can just be a refrigerator or something like that, and sometimes it's much larger. But this is the situation we want to model. And the point is that this whole universe has, and okay, so, and you can decompose somehow the universe as being the union of, well, it's sigma, the system, and with an environment. And how did I decide to call the environment? Probably capital. So this is environment. This is the system. And this is the universe. And then we can imagine that we are very clever and we know the dynamics of the universe. But we are only interested in the dynamics of the system. And you see that several things may happen. First of all, the dynamics of the universe, even if we know the Hamiltonian of the universe, it might be a bit too complicated to solve. But even if we are able to solve the dynamics of the universe, extracting what we are interested in for the system is also a non-trivial task, in fact. Yes?
We had lectures on effective field theories before. So in this case, we wanted to integrate out heavy degrees of freedom, for example. So
yes.
Is there in any way related to this?
Well, exactly. In fact, that was one of the examples I wanted to give, which is not exactly the same, is, for instance, you have, if you take statistical mechanics or whatever, we know the Boltzmann weights, so we know perfectly all the probability distribution of all the spins together, for instance. And indeed, we are interested only in two-point correlation functions, and computing them is hell, which is just a very, very tiny bit of the whole information. But it's very difficult to extract. So this is one of the examples, and the one you give of integrating over the heavy degrees of freedom, the heavy modes, is also an example of that. Yes, definitely, it's getting rid, and in fact, we shall see that the basic technique to get the information from the universe to the system is exactly, in nature, it's taking a conditional expectation, which is exactly integrating out degrees of freedom. We do not say that they are the most massive ones. It's not mass that decides it. It's something else, which is not the same in all systems, but definitely we want to integrate out certain modes, for sure. Okay, and so again, with this example, you can see that most of the time, this is too difficult. And here, in fact, extracting the information is very hard. Even if we knew, it would be very hard to extract the information. So the situation is complicated. And in fact, the theory of open quantum systems aims at developing tools to get effective descriptions of the systems. And in fact, there is a whole series of approximations. And if you want to have an idea of the kind of arguments you can give to get a coarser and coarser description of the system, by making more and more approximations. The first one is just to really deal with the initial problem. You have the full Hamiltonian for the universe, and then you do the job, you solve exactly, and you get the information for your system. So this is the head-on approach. And then there is a physical analysis of why you can neglect certain phenomena and go on. And in the end, the simplest, so you have some kind of linear organization. So where you have start with solving the full system. You go down. You have Markovian open quantum systems, which are the goal of these lectures. And basically, the next step is just isolated systems. Okay, so this and if you want to have a clear view, I could try to find the precise page, but if you look in it, you will find it. There is a very, very good and enlightening discussion of what is going on in Breuer and Petruccione, where they give a whole series of approximations. I would like just to mention one of those approximations, which shows that you, in general, even well, maybe I will say something about the scale just above Markovian open quantum systems on an example that maybe is familiar to many of you, that you can formulate either classically or quantum mechanically, because it's essentially the same. So imagine that sigma is coupled linearly to harmonic oscillators. Forming the environment. So if you think about it, what this means is that you have certain degrees of freedom. Let's say that x is the degree of freedom for the system you are interested in, and then these harmonic oscillators, they are the x alphas, and alpha goes from 1 to whatever. And because X is coupled linearly to harmonic oscillators, I don't put operators, but in fact the equations of motion would be the same classically or quantum mechanically. It doesn't make any difference. So basically, what you would find is that M alpha X alpha double dot plus omega alpha square. Okay, so these are harmonic oscillators. So let me suppress the mass. I don't really care about it. So I would have omega alpha squared X alpha is equal to something which is F alpha of capital X, essentially. And then you have equations of motions for X. And of course, using very, very easy, naive, one-dimensional Green function techniques, you can just solve for X alpha of t, knowing X alpha of 0, X dot alpha of 0, and F alpha of X at S for S less than or equal to t. If you know these things, you can solve for that. You plug it back in these equations, and you get differential equations with delay or whatever. Let's say integral differential equations for X. Which means that there is some memory. So X. So we have an autonomous description of X alpha of t, but in terms of the full past of the system.
Where is the linearity, sorry?
Well, the linearity is that you just have these equations. There is no X on this side. There is no, it's coupled linearly. So when you take the derivative.
Linearly for X, in little x? Or
in little x, yes.
Because the F alpha is not linear.
It doesn't have to be linear. It could be. It could even be. It doesn't have to, but well, of course, if it's linear, it's a bit simpler. It depends also on what you have for equations for X himself, but okay. So this is just this. This basically would be the one other level of difficulty, and you can go on up to having to solve the full system. Okay. But essentially, what we are going to do is concentrate on this level, and this means that the definition is that Markovian means is just that knowing the system at t, the state of the system at t is enough to compute it at time t plus dt. Okay, so this is what I understand by Markovian, and of course Markovian is a bit disappointing as a term because quite often, in fact, the equations are going to be deterministic. So in that sense, Hamilton's equations or the Schrödinger equation is Markovian. It's totally deterministic, but it just means that you just need to know the system at a certain time to predict its evolution in the future.
But in the case here for your x of t, it's not Markovian.
No, this one is not Markovian. That's what I said. That it was that I gave an example that was just above this. So we have where you have memory effects, and then you can do more complicated things up to solving the full system. Here it's one of the examples where you can really explicitly and in closed form eliminate the degrees of freedom of the environment. But this is not, and this is the last somehow the last case where you can do things in an analytical way, and then all the other ones involve more complicated things. Okay, so now I will essentially not try to argue why Markovian open quantum systems are relevant in nature. When a very bad answer is to say that if isolated systems are very good in certain circumstances, then finding something a bit more complicated has to also be good in certain circumstances. This is, of course, a very bad excuse. But I will show you that there are, in fact, certain settings in which the system is essentially purely Markovian. Again, this is always an approximation, but to an excellent approximation, it's clearly not isolated, that it's nevertheless, to an excellent approximation, Markovian. And you can do some kind of hand-waving arguments to say that, so imagine, for instance, you have a system which is in contact with a thermal bath, and you imagine you wait for 1 minute, and you can say, okay, now during 1 minute something has happened in my system, but if it's small, it has no consequence on the heat bath, so nothing has happened in the heat bath, and essentially the degrees of freedom with whom my system has interacted, they have most gone away, and they will never come back, essentially, and so the next minute my system is going to be in contact with new degrees of freedom, and so everything starts again like before. So these are the kinds of hand-waving arguments you can make to justify the Markovian approximations in some cases, but I will show you that there are certain definite physical situations in which being Markovian is really better than an approximation. Okay, so now we can, this is part of the motivations, so now I will say a little bit what is the approach we shall follow in the lectures. So the first thing is that I will first of all talk mainly about small systems. So sigma has just a few degrees of freedom. And also present things in discrete time. Start with a discrete time approach. And in this setting, I will try to derive, the aim will be to derive the general equations for Markovian evolution. And then, so this is basically, and then we will be left with two different things, which will be first, so understand the continuous time limit, and use the discrete equations or continuum equations to describe a few realistic somehow. Systems. And in fact, what I will mainly concentrate on is what I know best, and in fact it's related to observation of quantum jumps. So basically, what this means is, for instance, that you put a system with a few degrees of freedom in contact with the thermal bath. The thermal bath induces transitions in the system, and you observe the system in a certain specific way, and you're able to see these transitions as quantum jumps, just like, essentially, just like the Gedanken experiments that the physicists of the 100 years ago basically provided us with. Okay, so, but we shall try to give some other applications. So I would like to stress that the discrete time approach is essentially for pedagogical reasons. I think it's really easy to see what is going on in discrete time. So this is essentially, and the concentration on small systems is pedagogical somehow, but it's also realistic because among these Markovian open quantum systems, some of them are in the lab are just devoted to build quantum computers or to do quantum metrology or whatever. And these really, for these systems, really, small systems are a good example and are not uncommon in labs. And in fact, well, I take the opportunity to make some advertisement. So next week there will be a very interesting conference just in the room, which is about the manipulation of simple open quantum systems, and which will, I invite those of you who are interested to attend, because this is clearly, there will be many talks that are related to what I'm going to tell during the lectures. What else did I want to say about that? Yes, there is one. Okay, so this is important. So the fact that people dream of making quantum computers, in fact, and think it's not just a dream, even if it's very far ahead still, I believe, is that there has been a tremendous progress over the past decades in two things: the mastery of low temperature physics, which allows to have systems which are not totally isolated, but nevertheless that survive long enough so that you can make observations on them. So low temperature dynamics, the mastery of low temperatures. And the second one is fast electronics that allows you to make measurements in no time, essentially. So this has made it possible really to manipulate in labs. I will show you some experimental setups later on, small systems, and to do really very extremely beautiful and delicate experiments which test really the basic principle of quantum mechanics on the one hand, and on the other hand are close to technological applications. So I think it's a very, very beautiful subject, if only for that reason. Okay, so so now the idea is, when I say derive, is that we are going to start from the basic principles of quantum mechanics, and we shall try to see what they give when we impose some kind of Markovian principles. So this is going to take some time, and before embarking on this, which is a bit arid somehow, I would like just to give you essentially the main equations that we shall be working with during these lectures, because deriving the equations can be a little bit painful, but contemplating them and seeing that they are reasonably beautiful is something you can do immediately. So let's do it. in fact, maybe this is even a good time if there are questions before I go on. No questions? So there will basically be two facets, let's say, which will be for evolution in average. And then for random evolution. And the first one is easy. We have a density we have a density matrix. So this is based on density matrices. So this, I take this occasion to make some kind of pool in the audience. So is everybody familiar with density matrices? Fine. Partial traces? Fine for everybody as well? Perfect. You're probably more at ease than I am myself. Anyway. So this is in the framework of density matrices, and you consider the following transformation, which is you have a density matrix rho, and you transform it in the following way. Rho prime, which I also call psi of rho. This is just a notation, but this is more explicit. It's going to be a sum over A of VA rho VA dagger. So you have then you have of course some Hilbert space somewhere. You have a density matrix, and you have some operators. On H, and this is a transformation. And you see that indeed, and so, in fact, so the theory we want to make is just the theory of the iteration of the map psi. Yes?
The system to which your system is coupled, is it classical or quantum also?
Quantum also.
Everything's quantum.
Everything is yes. Well, I guess you could do well. You could take the classical limit for some. But here, this is just describing. If you want, this would just be H sigma, and this would be rho sigma. If you want. This is just. You see, this is just an autonomous evolution for rho sigma. This is just about the system itself. Okay. So this is an equation that is an effective equation that has been obtained by averaging essentially over the environment.
Is the sum finite?
It's okay. So in these lectures, the sum will always be finite, and then there are theorems. It can be countable, in fact. Yes. It's yeah.
What do you assume on V?
Nothing. Nothing. But okay. So maybe I should say I'm interested in small systems with a few degrees of freedom, and for me, a single harmonic oscillator is already many degrees of freedom. So I deal only with finite dimensional Hilbert spaces. So if you do okay, so if you want to do mathematical generality, this guy can be infinite dimensional, and then this sum can be countable. If you, like me, you deal with systems having a finite dimensional Hilbert space, then you can also do a countable sum, but in fact, there is a theorem that I will say a few words later on, which is choice theorem, which tells you that in fact, you can do basically with at most the square of the dimension of H as the number of operators here. This is the most general. Okay, so I will maybe I will have time to show you this theorem, or I will give it in the notes somehow.
So is it obvious that the new density matrix is a valid one?
No, because there is one equation missing. This should be supplemented with another equation, which is the following, that sum over A, VA dagger, VA is equal to the identity operator from H sigma. And this is this ensures the conservation of the trace. Okay, so it's easy to see if you compute the trace, you use cyclicity, so this is why the V dagger is on the other side this time. And if this is to conserve the trace for every density matrix, then this has to be the identity operator.
But what is the physical meaning of this VA? Is it evolution? I mean,
Well, as I said, we want to make the theory of iteration of psi, and this is just this is just the evolution between t and t plus delta t, if you want. T equals n plus 1. And of course, you just iterate. And of course, you could imagine situations in which these operators are time dependent because the environment is changing or whatever. But you could imagine all situations. Okay. What else should I say? Okay. So, I will say it later on. So, you see, so this you can think of this as very dull somehow. And indeed, it is. So you see, this is just a linear evolution equation. So if you go to a basis and all that, this is just applying a matrix to rho. And so solving the system is just essentially diagonalizing a matrix. You see, this is psi is a linear transformation. So essentially, the job is just diagonalize psi. Okay. So I take this opportunity to introduce some vocabulary. So I think the vocabulary itself is very bad, but it's good to have a name nevertheless. So psi is what is called a super operator. On H. And this means that it's an operator on operators on H. So that's why they call it a super operator. I think the name is very bad, but it's good to have a name for this kind of things. So let's call it super operators, as everybody does. I mean, this is the standard. Okay. So we want to diagonalize psi, and I will show you in 1 second that in fact psi has one of its eigenvalues equal to 1. And the others one can show. In fact, I don't know the proof, but one can show that all the other ones are smaller than one in modulus if you have these hypotheses in force. So we want to diagonalize psi, and then we compute completely the evolution. So from a mathematical viewpoint, this is just very, very simple. Okay, so you can think of this as a trivial task somehow. So let us make some very simple remarks. The first remark, okay, so the first remark is how to find solutions. So the one thing one has to do first of all is find solutions to start. Okay, I will provide you with one, and it's the following. It's just take that there is only one V. And it is unitary. And it's reassuring to see that indeed in that case, what you see is just what you know from standard quantum mechanics. Then this is rho gives V, rho, V dag, where V dag V is equal to the identity. This is the standard unitary evolution from quantum mechanics. Okay. So, so even if the task is trivial, one has to keep in mind the real difficulty in that case which is find physically relevant families of V's. You have a system to study and you want to find the V's which are physically relevant. So maybe we are not so much used to this today, but in the old days of quantum mechanics, finding the correct Hamiltonian to describe a system was a totally non-trivial task. And still today, finding the correct V's is a totally non-trivial task for Markovian open quantum systems. This is something you have to do. There is one observation is that, so this equation, so let's call it this equation is called the master quantum equation because it's the analog of the equation, what is called the master equations in Markovian systems, classical Markovian systems, where you have, so, okay, so let me say a few things more. I will erase later on. Okay, let me use this. So, first of all, so there is one remark that one should make, is that the diagonal, if you choose a basis, and then the diagonal of rho is a probability vector. From the rules on density matrices, the diagonal elements are positive and non-zero. So, I'm sorry, and sum to 1. So this is going to be a probability vector. And so you see that this is why you talk about a master quantum equation, because this is a generalization of the classical master equations for quantum, giving the evolution of a probability density. Here it gives the evolution of the density matrix. And then you can ask, and you can check, of course, that, okay, so then you can ask which choices of VA are such that rho prime diagonal part depends only on rho diagonal part. So this is a good question, and it's quite general, but you can think about it for yourself, and then you will discover at least then the diagonal evolution is that of a standard Markov chain. And conversely, you can realize any Markov chain that way if you want. And any Markov chain can be realized. You can view this as an exercise for you. I will give the solution in some later lecture because it's useful in certain situations. So, in fact, if you give me a classical Markov chain, I can find VAs such that the VAs are going to leave the diagonal, be such that you can express the new diagonal in terms of only of the old diagonal, and have the right dynamics.
Excuse me, if
Yes.
it's not too long, can you just rewrite the classical master equation of which this is the quantum version?
Yes, I can.
Okay.
Yes, we can. So the classical equation would be that pi prime is equal to a certain matrix pi times p. This would be a vector, probabilities, and p would be a classical stochastic matrix. So what I'm saying, I can rephrase what I just said. If I have a choice of VAs which is such that the diagonal of rho prime depends only on the diagonal of rho, then the evolution for the diagonal will be of this form with a stochastic matrix that can be expressed in terms of the V's. Thank you, André, because indeed I wasn't clear. Okay, so this is the first question, and in fact there is another good question which is important. For the rest of the lectures, because it will play some role, which is which choices of VA are such that rho prime is diagonal if rho is diagonal. It's not the same question. Okay, so this is another. Okay, so this is just in the. I have given you one solution to these equations. I tell you that you can find many more which are related to classical Markov chains. And just to make contact, because I guess is it allowed here to give lectures without mentioning random matrices, or I will give one last little thing, which is the following. So imagine that each VA is of the form PA, UA, and this one is unitary, and PA is a probability vector. And I'm wrong, here is square root of PA. So okay, so this is another solution, which is not a unitary evolution, but which is valid. And some okay, we'll say a few more words about it in a minute. Okay, so now that I've said a few words about evolutions in average, I would like to talk about random evolutions. And here the situation, so here somehow, to say it again, the mathematical situation is essentially trivial as long as, if I tell you, okay, this is a 10 by 10, this Hilbert space has dimension 2, essentially we will do all the lectures with the system has a Hilbert space of dimension 2. That's enough to make interesting things.
Aren't PAs constrained by detailed balance considerations or things like that?
They don't.
No, you don't care?
You don't.
Okay.
You don't. And sometimes they are not, definitely, constrained by that. And sometimes they could. And in fact, by the way, that's a question you should ask Dennis, because he thought about it. He has some equations expressing the meaning of detailed balance for the VAs. This is not totally trivial. And okay. So again, once you have these formulae, it's essentially trivial to solve them as long as the Hilbert space is not too large. You just put it on the computer, and the real difficult task is to identify the correct VAs that do the job. And indeed, if you think about it, I wrote here, so you know, it's been fashionable for the last 10 or 20 years to use Markovian Markov chains or Markov processes to describe non-equilibrium systems. And again, the choice of the right P to describe a system is totally non-trivial. I mean, this is something there are very few guides to say, okay, my system has these physical features, what should I choose for P? This is essentially terra incognita. It's really something you do by hand for each system. You think about it and you say, okay, this is the matrix P I want to use. You can use detailed balance if you want, see if it's if the system is at equilibrium or you want it to go to equilibrium. But in general, finding the right P to describe a certain physical situation is something non-trivial, and just the same. Okay, so let's go to the random case now. So the case of random evolution is the following. So first of all, this summation, we will keep the same operators VA, and then we will imagine that they are we have to say something about the index set, and we have to say that. So we say that A belongs to a certain set which is finite for me, which is S. And to do the random evolution, you have to add more information. First of all, you have to partition S. So you split S in different pieces, okay? And then you generalize this equation in that you say that rho, I suppress for a time being, I suppress the subscript sigma because we are just talking about the system anyway. It's going to be rho prime, which is equal, so sum A belonging to SR. I need to make sure that I write down the equation correctly. Yes, I'm doing it correctly. VA rho VA DAG. I divided by trace of sum A belonging to SR VA rho VA DAG, and with probability pi r, which is just equal to trace sum over A belonging to SR VA DAG. So these are the equations for a random evolution. And so essentially, well, this is really the top of the mountain that we want to reach, is this equation, and I'm very pessimistic, you see, I'm just writing. So this is basically the top of the mountain that we want to climb, is getting to these equations. And because these are the most general equations for Markovian open quantum systems, essentially. Okay, and then you see, so now this time, the mathematical situation is a bit less trivial than before, because now this is the iteration of A. It's more complicated than before, because first of all it's random and it's nonlinear. Okay, so you have rho 0 goes to rho 1, blah, 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 rho 2. But all this is random because it happens with a certain probability. Okay, so I will, I suggest you to play this game. You see, okay, so exercise or suggestion. Is just to put this on the computer. So imagine, for instance, that S has a cardinal which is just equal to 2. Imagine that H is just C2, so it's a two-dimensional Hilbert space. and you find some solutions for these equations. So you find V1, V2. The only constraint being that one. And you can use this, for example, or whatever, and you can do this iteration. So, find V1, V2, and then look at trajectories on the computer. So there is a name for this evolution. This is what people call a quantum trajectory. You know, we all learn in basic quantum mechanics that trajectories of particles do not make much sense. But here it's a trajectory. It's a perfectly well-defined trajectory of a dynamical system. It's a trajectory on the space of density matrices. Okay, so put it on the computer, and in fact, there is a wealth of possible behaviors, and for many of them, there is interesting physics behind that I shall try to explain in later lectures. I would like to add that there is, and in fact, somehow, the case I mentioned that you could do in the linear case that you could do Markovian evolutions, and you could also use these things which amount to random matrices. In fact, if you look at this situation in that case, you will see that in fact what you are doing is that you just imagine you have a system, and at each time step you choose in a random way which unitary evolution you impose to it, so that the evolution is a random succession, and each matrix UA is chosen with probability PA, and so you have a product of matrices. So it's of course it's a bit different from what you do usually in random matrix theory, because as the matrices are unitary, in disordered systems, because the matrices are unitary, so the product is still unitary. There is not it's hard to find really a Lyapunov exponent, but nevertheless there are other things, interesting things, and in particular you see a product of matrices, and you can ask yourself how it behaves, the trajectory it draws on the group itself of unitary matrices, and how dense it starts to feel and all that. And there is nevertheless some kind of mixing time and all that, and so there are nevertheless interesting exponents in this setting. But anyway. These are in some sense the least interesting examples, Markovian type or unitary type, but find intermediate solutions, iterate. And I would like to add that there is one thing, in fact this should be supplemented somehow with one interesting thing, which is the result of this here. And so you have counting processes, and S. This is not a very good way to write it. Let's call it NR, and NR becomes, R prime becomes NR prime plus delta R prime the same by R. So these are counting processes. And these are these you see when you iterate this map, each time you have to choose one of the R's. It's chosen with a certain probability pi R, and keeping track of which ones is something that is wise for two reasons. The first one is that these equations, in fact, if you think about it, they are related to measurement. These equations. In fact, if you think about it, what else in quantum mechanics do you know that is not linear? At least for me, the most natural thing which is non-linear and gives a random output, it's a measurement in quantum mechanics. So these are related to measurements. Somehow, the A's, they label the possible outcomes of the measurement, and we group them in pieces because somehow we decide to forget about part of the information we've collected in the measurement. So we put them together in pieces. So this is what we keep from the information that we collected, that was collected in the measurement. And of course, it's good. It's a good idea. It's wise to keep track of what has been the outcome of the measurement, what you have kept as information at each time step. So this is, of course, the prime is it's terrible. Let me put a tilde here. So this is just counting the number of times the outcome of the experiment has been R. This is another way to say it. Okay. And I will finish for this first session with just a little remark, which is the following, that you see that this is, okay, so all these equations are classical. Then these are classical dynamical equations. And in fact, we shall spend most of our time solving them numerically or giving arguments in certain limiting asymptotic circumstances to say what happens to this dynamical system. But this is a classical dynamical system. And one of the ways to see that this is classical is that these here are just classical bits which take value 0, 1. Okay, so this here takes value 0 or 1. But in fact, there is a somehow higher level description with quantum randomness what are called quantum noises. And I will try to talk a little bit of that during the last lecture. But essentially, to say things in words, and especially for those of you which are familiar with quantum computing, in fact, you know that you can do a classical computer by manipulating bits, and then you can do quantum computing by manipulating qubits, and we shall make exactly the same step for Markovian quantum systems. It's very easy and natural. So we shall transform these processes, which are classical processes, in processes which, instead of taking value as classical bits, will take values as qubits.